Okay. Good morning, everyone. I'm sharing the QR code. Give the attendance and we will start. So 9 students are present. We will not waste much time. We will start. Wait. I think everybody has given the attendance. Okay. Now let us come to this portion. Yesterday we have discussed about Anderson. Okay, we have discussed about Anderson. Today we will discuss about de Sauty. But before going to de Sauty, let us discuss about some of the important parameters which we will require here. First is dissipation factor, D. What is dissipation factor? This is important. Okay, a practical capacitor is represented as series combination of small resistance and ideal capacitance. For a vector, now dissipation factor is an important term. Now, you have many times you have learned this word dissipation, that heat is dissipated. Okay, like that. So, what is dissipation factor? Dissipation factor, till now we have read many bridges, right? But we haven't used this word dissipation. Is my voice audible? Ayushi, just please confirm me. Hello.
Yes, ma'am.
Actually, if my voice lags, please tell me, okay? क्योंकि सुबह से आज Zoom का थोड़ा problem है. My voice is lagging many times. That is why I'm telling you. Okay, so dissipation factor जो है यहाँ पे use हुआ है. So till now we have consulted many bridges, right? Maxwell, Hayes, Anderson. But we haven't come to this word dissipation. So dissipation factor is a measure of the loss rate of energy of a mode of oscillation in a dissipative system. So you can say that it's a reciprocal of quality factor because we have learned quality factor here. Q factor we have learned. Okay, so we can again say dissipation factor is a reciprocal of quality factor. Okay, so dissipation factor is important to regarding here in this case. Now, if dissipation factor again have you can express it with the help of this vector diagram. It is seen that angle between the voltage and the current is slightly less than 90. So angle, this is called loss angle. So loss angle is also a term here. It is been used. And here see a capacitor or a condenser. This kind of, this is the capacitor or condenser have been attached and through which current is flowing as well as voltage. Just have drawn to show you, that where the dissipation factor needs to be considered. It's a picture of a practical capacitor. See, a resistance has been connected with the capacitor and voltage VR is there. The voltage across C is there. This is total voltage. So it's written here, the representation of a practical capacitor. Okay. Now come to this picture. This picture, if you see, you can see here, this picture is depicting, it is depicting the, what to say, the both the dissipation factor as well as the loss angle. I'm enlarging this picture to make you understand. Follow this picture nicely. Okay. What is in this picture? Wait. See here. First of all, definitely current is here. This is my VC, means the voltage across the capacitor. Okay, this is my IR, this is my VR. Now, they are taking that the loss angle somehow to 1 degree to 5 degree. Okay, and here they have taken the resultant of this vector V here, means this is a VR, this is VR, this is VC. Then resultant of the vector will be V, this one. So they have just jointed with the dotted line. This is completely vector representation. So I think you all have learned in physics in class 11, 12 about the vector representation. So if you are asked to write, and where is the loss angle they have denoted? The loss angle have denoted somewhere here. And this total is 90. Okay, this total is 90. Then only this much will be 90 minus this loss angle, which they have shown here. Okay, now if you are asked to write what is the tan, what is tan del, this thing means del is the loss angle here. So what is the formula you can write, which I can see? I can write tan del will be definitely IR, okay, IR divided by IXC. So I can see, I can write this. So II will be cut down. So I will get R by XC. Okay, R by XC. Then I can, if I want to convert it into in terms of, you can say, wait. In C, it's written here in terms of dissipation. So we can write here, I'm clearing the drawing here. Yeah, we can write here D equals to omega CR, D is the your dissipation factor. And I told you dissipation factor can be also termed as a reciprocal of the quality factor. So we are writing D equals to 1 upon Q. Okay. So this dissipation factor, if I say D equals to tan del, then tan means sine upon cos. So we can also write that sine del equal to this tail angle, and cos we have, if we take it 90 degrees suppose, then obviously cos 90 we are taking 1 and here we are taking del. So we can somehow write at some point of time the dissipation factor is my voice audible? Hello, Ayushi, एक बार confirm करो. Josna, Pooja. Hello. Hello. Is my voice audible? Hello. My voice is audible. Please tell me.
Ma'am.
Okay. Actually,
Yes, ma'am.
yeah, thank you. So see here what I was telling, that to some point of time, I need to show you that that here as quality factor, the reciprocal of Q factor is dissipation factor, and dissipation factor is somehow equal to loss angle. Okay, this is the main motto to prove it. Okay, that from this vector diagram where we are denoting the tan del, or we will denote this term as del. And dissipation factor D can be written as sin del by cos if we take it 90 degree. So at some point of time, we can write the dissipation factor is somewhere equal to the loss angle. So this will be my main motto. Now let us move on to the next part, that is D-sortie. D-sortie bridge. So let me first show you the diagram. This is my D-sortie bridge diagram. Okay, so I think it is visible to you. Achha, one more thing, let me tell you. Okay, now D-sortie bridge, you can say it is the most suitable bridge for comparing two values of capacitor, because you see here we have already connected here two capacitor. One is capacitor C1, one is capacitor C2. So we will try to compare these two capacitors here. And mainly here we use D-sortie to measure capacitance, right? Because this total D-sortie actually starts from the measuring of the capacitance and loss angle. Loss angle come from dissipation factor. Okay, so we will concentrate on this particular diagram. And here you remember one thing, we are neglecting the dielectric losses in case of bridge circuit. So this is the picture of the D-sortie bridge, which has been shown here. And you just check it out here. One more thing you need to see, this is the I1 current flowing, this is the I2 current flowing, and this is C1, this is C2, this is you can take, this is terminal 1, this is terminal 2, this is terminal 3, this is terminal 4. Okay, and this is the R3, which is somehow variable, and this is R4 is also variable, and this is E1, E2, E3. Okay, so this is the common put, and the supply is here, you can say it is termed as E. So this is the D-sortie bridge. Now see here, battery is applied in between terminals, which is marked as 1 and 4. Okay, so here battery is connected. So here one battery will be there. And arm 1 and 2 here, it consists of capacitor, this C1, whose value is unknown definitely, but it carries current I1. And arm 2, 4, here a detector is connected. Sorry, arm 2 to 4, yes, detector is connected. And where are the purely non-inductive resistors are connected? It's on 2, 3 arm and 3, 4 arm. You can see here. And definitely on the 4, 1 arm, another capacitance C2 is connected, which is a standard capacitor whose value is already known to us. That means the C1 value is not known to us, but the C2 value is known to us. So we need to derive the expression for the capacitor C1 whose value is unknown to us. Okay, this one. So because C2 value we know, so we need to derive the expression for the capacitor C1 in terms of the standard capacitor and the resistor. So you can tell me what will happen in case of balance condition if we try to balance this thing. So according to me, I will get something. Wait. I should get the formula will be like this. I mean, at balance condition, it will be somehow 1 by j omega C1 multiplied by small r4. You can also take capital R4, because here in this picture I have mentioned this will be small. Keep it as small R3, R4. Then it will be easier. Okay, and this will be 1 by j omega C2 R3. Okay, it will be somehow like this. So it implies that the value of capacitor can be given by what? So C1 we can write C2 R4 by R3. Okay, R4 by R3. So I need to find the value of C1. So in order to obtain the balance point, we must adjust either R3 or R1 because R4, sorry, either R3 or R4 because both are the purely resistive. And we need to adjust R3 and R4 without disturbing any other element of the bridge. So this is the most efficient method of comparing the two values of capacitor. Remember one thing, if all the dielectric losses are neglected from the circuit. Okay. So now you can draw a very basic phasor diagram from this particular simple D-Shorty bridge. What kind of phasor we can have? I'm drawing here. So this kind of phasor we can have, see here. So I need to get the resultant. So see, in phasor or vector, you have to get a resultant. So here it will be E1 equal to E2, and here will be E3 is E4. Okay, so this will be my resultant. So my phasor will be somehow like this for this simple D-Shorty bridge. Now, so here what I have done, I have marked the current drop across. So what we have to do next, our next process starts a bit different. We need to modify the D-Shorty bridge. So we have to mark the current drop across the unknown capacitor, that is E1. So voltage drop will be across what? Across R3. That will be E3. Again, voltage. So remember one thing, the current drop across unknown capacitor will be E1. Okay, voltage drop across the resistor R3, that will be definitely E3. And voltage drop across the arm, across the resistor R4, that will be E4. Is my voice audible? Please confirm. Ayushi? Hello. Ayushi, Pooja? They are not responding. Hello? Hello?
Ma'am, it's not clear.
हाँ, इसलिए मैं पूछ रही हूँ ना, I'm asking you ना, just tell me what is the condition because it's showing me that my internet is unstable. That's why I'm asking you. अभी ठीक है? Now it is okay?
Yes, ma'am.
Yes, ma'am.
Okay, ठीक है. मुझे confirm करो वरना मुझे problem होता है ना. पूजा, आयुषी, बताओ तो अभी ठीक है मेरा वॉइस? कंफर्म करो एक बार. Is my voice lagging still now? Hello? Josna? हेलो, देखो तो अभी ठीक है वॉइस? नाउ इट्स क्लियर? हेलो?
Yes, ma'am.
हाँ, when I ask you ना to respond. अच्छा, ठीक है. So what I was telling, now we have to understand the drop. So let us mark the drops here. So first of all, I told you that across this, the current drop across this capacitor is E1. Okay, voltage drop here will be definitely E3, and here again the voltage drop will be E4, and here the voltage drop will be E2 for the capacitor C2. So at balanced condition, the current will flow through the path 2 to 4. That means this one is my terminal 1, this is 2, this is 3, this is 4. So at balanced condition, the current will flow in this path, isn't it? So the voltage drop will be the voltage drop will be E1 and E3. That means the voltage drop at balance condition, the voltage drop E1, E3, okay, that will be equal to the voltage drop E2, E4. This formula is during the balance condition. So again, so likewise that I have drawn the phasor. So phasor मैंने दिखाया था, the phasor तो मेरा law. I'm again drawing that phasor for you. So this is the thing. This is my resultant E, and here you can take it as E1 equal to E2, and this is as E3 equals to E4. Okay, E3 equals to E4. And this is my phasor. This is my phasor. Okay. So in order to draw the phasor, I have taken the axis E1 and E2 on one side, and definitely E3 and E4 on the other side, so that it can make an angle of 90 degrees. Because
Voice clear.
wait. अभी ठीक है voice? बताओ तो. I don't know, today my internet is very bad. अभी ठीक है voice? Now it is okay? Hello?
Yes, ma'am. Yes.
आयुषी थोड़ा बताओ, थोड़ा respond करो.
Yes, ma'am.
अच्छा ठीक है because Sushila told me my voice is not audible properly. ठीक है. So now what we need to do, so this is all about the basic structure of phasor. Now there are some advantages and disadvantages. Some advantages are like is that this bridge is quite simple and provide easy calculations, but this disorderly structure has some disadvantages. Why? Because this bridge actually gives inaccurate result. First disadvantage is that this bridge give inaccurate result. Okay, inaccurate result. First. Second disadvantage is that and this inaccurate result is for imperfect capacitor. Imperfect capacitor. Okay. And here imperfect means definitely which is not free from dielectric loss, remember. So hence we can use this bridge only for comparing perfect capacitor. So this imperfect capacitor will not help. So we can only use this bridge for perfect capacitor. Okay. So now we need to modify the de Sauty bridge. How we will modify it? Now we have to modify this de Sauty bridge. Why? Which can give us accurate result for imperfect capacitors. Okay, and this modification is done by Grover, a scientist's name. The modification has been done by a scientist whose name is Grover, Grover. This scientist had made this particular de Sauty bridge circuit a bit complex one. So let us come to that complex diagram. I'm moving to my next slide. So this is the most modified. I think this is visible to everyone. This is the most modified de Sauty. Modified de Sauty. So see here, what are the modifications we have done or Grover has done. Let us check it out. See, first of all, they have connected, hence Grover has introduced what? Electrical resistances R1, R2 in the arms. If we take it as arm 1, arm 2, and arm 3, arm 4, or you can also write it as A, B, C, whatever. So see here, R1 has been inserted here in the arm 1, 2, and again R2 has been inserted here in the arm 1, 4. That means in the previous picture, C1 and C2 are independent. Abhi yahan pe हमने R1 and R2 we have connected in order to include the dielectric loss. So now we will include dielectric loss. Again, he connected resistance as R1, capital R1 and capital R2 resistances in the arms 1, 2 and 4, 1, whatever. So let us derive now the expression for the capacitance C1, which is definitely a value as which unknown to us. So we can connect the standard capacitor on the same arm. Okay. So as we have done in de Sauty bridge. So now what is the voltage drops we can have? What is the voltage drop we can have from this new modified diagram? I can see definitely R1 plus small r1 plus 1 by j omega C1. Okay, in bracket you can take here R4, that will be equal to capital R2 plus small r2 plus 1 by j omega C2, and in bracket you can take R3. So I think this is clear, this much, where when we are taking the voltage drops and on balancing point, this is my equation. So if we solve these two equations, I can get on solving, I think I can get C1 by C2, that will be equal to definitely capital R2 plus small r2, and this will be capital R1 plus small r1. That is equal to definitely R4, R3. So this is my required equation. So from this equation, I need to make a phasor which can calculate the dissipation factor. Okay, so let us move on to that. So the phasor diagram, let me see whether the phasor will be very simple. So let me show you here the phasor. How it is simple. So first of all, you have to draw like this, just like the previous phasor. Okay. So you will get some resultant here. This will be my resultant, and that will be E. Okay. So, so here some of the voltage drop across the capacitor C1, C2 you have to draw. That will be somehow here. Okay, this is the two capacitor. This is obviously EC1 and this is EC2. Then you have to definitely join this, and you have to again. So this similar kind of picture let me show you here. Wait, let me clear all this and let me take you downward. See, I hope this picture is visible. So this is the modified de Sauty bridge phasor diagram. So finally we have obtained what? Let me write here the formula. C1 by C2, that is equal to R2 plus R2 divided by R1 plus R1, that is equals to R4, R3. Okay. So this is the required equation, and from the required equation, we have tried to draw this phasor diagram. Means Grover has tried to draw this. So here it is I1, R1, right? Similarly, for this one, we have done for only not only this E1 I have said E1 is equal to E2. So अगर तुम्हें draw करना है तुम ऐसे I2 R2 के लिए भी draw कर सकते हो. Okay. So and we also know E3 is equal to E4. Okay. So all these are connected. This is the resultant E you see here. Resultant E means simply. So E is here what? E1 is a vector quantity plus E3. It's a vector quantity. That will be, sorry, that will be equal to, that will be definitely equal to what? That will be equal to E2, which is again a vector quantity plus E4. Okay, it will be somehow like this. So this is, so let us, now from here we have to mark the phase angles, okay, of the capacitor. So phase angle of the capacitor, that is del 1 and del 2 of the capacitor C1 and C2. So C1 will be having C1 will be having the phase angle that is del 1, and C2 will be having the phase angle del 2. Okay, so if we have the from phasor diagram, we can write the dissipation factor. So let me take you to that. Wait. So this is my phasor diagram. Wait. Achha, they have not shown here. So let me show you. So this is my phasor diagram, right? So let me share my whiteboard with you. Then it will be easier. Achha. Phasor diagram to wahi hai, which I showed you. So from the phasor diagram, we can write tan del 1, that is equal to the dissipation factor that will be equal to omega C1 R1 because of the arm, that one which is having capacitor C1. Similarly, we can also write for 10 del 2 dissipation factor that will be omega C2R2. Clear? So from the equation 1, what was equation 1? Equation 1 was, let me tell you again, equation 1 was like this, R1 plus 1 by j omega C1 R4, that is equal to R2 plus 1 by j omega C2 R3. This is my equation 1. So from the equation 1, I can write, we can write C2R2 minus C1 R1, that is equal to C1 capital R1 minus C2 R2. Okay. So now if we multiply omega on the both sides, because we will consider here dielectric losses, right? So if we multiply omega on both sides, then what can we have? Then we can have omega C2R2 minus omega C1 R1, that will be equal to omega C1 R1 minus C2 R2. Okay, so this is one again, but we know from the previous equation what we know. We know that, but we know C1 by C2 is equal to R4 by R3. Okay, this is my no. So therefore, my final expression for dissipation factor, because from the modified de Sauty bridge we can obtain the dissipation factor, that will be definitely tan del 1 minus tan del 2, that will be equal to omega C2, in bracket you can write R1 R4 by R3 minus R2. So this will be my required equation for dissipation factor. Hence you can write, if dissipation factor for one capacitor is known, so we can write here that if this dissipation factor DF of one capacitor is known, then what will happen? Then this method will give inaccurate, definitely some sort of results for dissipation factor. So from this kind of de Sauty bridge, from modified de Sauty bridge, we can obtain dissipation factor. Now let me take you to my notes where I have done the same thing. See, more or less same thing have been done here, and we have segregated the real imaginary part, and ultimately we have got here also a dissipation factor. So you see here the dissipation factor which I obtained, same process I have done. So D equals to omega, D equals to what? D equals to omega C1 R1. Okay, so this thing you will obtain if you segregate the equations, because finally from my, in the whiteboard what I have done this tan del 1 minus tan del 2. So this process you can also do, and whatever I have done in the whiteboard, that you also can do. So advantages definitely are there. This R1, C1 are independent of the frequency, and sources need not be pure sine wave. And definitely this modified de Sauty is all about, you can say it is of correct the inaccurate result. Okay, correct the inaccurate result, and which we are not getting from the simple de Sauty. So see what they have done here. Let me tell you once what they have done here. Suppose from the arm 1 and 2, what we were getting? We were getting the capacitor. With the capacitor, newly they have joined two resistances.
Mommy, your voice is lagging.
Yes. Wait. अभी देखो ठीक है? अभी मेरा voice is clear now? थोड़ा confirm करो.
Yes, ma'am.
Okay. So देखो यहाँ पे R1 को कैसे लिखा है? R1 dash, this is R1 dash. R1 dash, they have R1 plus R1. This is for capacitor C1. ठीक है? R2 dash को they have taken R2 dash, they have taken R2 plus R2. This again for capacitor C2. So these two equations you know, that is the balance condition में हमने लिखा था. right? So R1 का वैल्यू मुझे पता है, R2 डैश का वैल्यू मुझे पता है, since they have only cross multiplied, sorry, did the multiplication, और यहाँ से they have segregated the real term. What is the real term? Real term is R1 dash R4 and R3 R2 dash. Okay. So after segregating, we have got R1 dash is equal to R3 R2 dash by R4. Again, I know what is my value of R1 dash, it's R plus R1, and R2 dash is this one. Okay, so you can follow this formula also. This is, I think it will be easier for you to find out dissipation factor. अब नीचे देखो, नीचे क्या है? We have compared the real part. Now we should compare the imaginary part. ठीक है? Imaginary part कौन सा है? Imaginary part को हमने ले लिया है, that is R4 by omega C1, R3 by omega C. तो यहाँ से मुझे I need the value of unknown capacitors, that is C1, right? So this is I have taken, that is R4 C2 by R3. Again, I told you that what is my Q factor? Q factor, you know what is the formula of Q factor, and dissipation factor is the 1 by Q, reciprocal of Q factor. So similarly, first I need to write what is Q factor, और जो भी आएगा Q factor में उसको just हम वहां से we can find out the dissipation factor. So this is my dissipation factor which I got, that is omega C1 R1. Okay, so this is all about D-Sorty. So D-Sorty has two particular diagrams to understand. One is the simple, second is the bit complex one with resistances in the with the capacitance. Okay, so this is the thing. Now you can follow this derivation also, which I have done. Any one of the two, both are correct. Okay, both are correct. If you feel good, you can do. Not an issue. जो तुम्हें अच्छा लगे तुम लोग कर सकते हो. This notes I will give you. Don't worry. Once I finish the scaling bridge, I will give you. So after this Anderson, we are having I think Wiens. We don't have scaling. Maybe I have to check the syllabus. हमारे पास Anderson D-Sorty के बाद we have I think Wiens. So Wiens is somehow, so all these bridges now they are comprises of capacitors and resistances. So you see here एक simple bridge होता है, complex होता है. तो complex जैसे कैसे बनता है? It is made from the addition of resistances. Okay, so अच्छा, who are left from giving the attendance? So give the attendance ones who are left out. And any query you have, you can ask. Upload, I will upload the video, go through once. तो दोनों equations से तुम्हें मिल जाएंगे, मेरे वीडियो से दोनों derivation मिल जाएंगे. The dissipation factor is the main thing to find out. ठीक है? तो dissipation factor is the main thing that we require to find out from this D-Sorty. तो videos तो मिल जाएंगे. अभी के लिए videos check करो. Or if you feel, you can also prepare your own notes. I will give the notes after I complete these bridges, all the bridges. Okay. So thank you so much. So if you have other attendance, if you have given, then you can leave the class. Okay. Thank you so much and have a nice day. We will again meet on Thursday.